started recording. Since last week, what has changed? You guys have submitted homework 1, I believe. Any feedback? How was it? Easy? Not enough questions? Not long enough? Or not difficult enough? Is there any feedback for me and the assistant team? Nothing? Okay, so not hard enough, I guess.
Quite hard, miss.
Really? What did you find difficult, Saddam?
The last question.
I don't remember by heart. Which one is it about?
It's the finding the number of suicides with the population.
Oh, so you had real data, right?
Yeah, so it was unusual, an experience, I guess.
Yep. Okay. So that's great. Thank you for your feedback. Yes, I did actually ask the assistants to prepare real data because it seemed kind of pointless for me to like use the basic like height and weight and so forth. So since you will eventually, hopefully, use the knowledge obtained in this class for doing exactly that, which is computing real data, we did intentionally use some real data. I think it was a Kaggle data set. Am I correct? I think it's from Kaggle. I think so.
Yeah, I think so.
Yes. Okay. Well, who knows? Maybe one of you would like to join Gemastic. Have you heard that competition, or maybe other types of competitions of data analysis? So, by the way, I am one of the contact persons for data mining. So, if anyone is interested, you may contact me if you want to join. So, anyway, I will now start the lecture. I will continue first where we left off. So this was the menu last week, right? So we talked about the sample space and events. We talked about the basic algebra of sets, the algebra relations of sets. And we had some axioms that we want to prove and fulfill and follow while we process the probabilities. Then we left off lastly on conditional probability. And I promised that this week we would continue on to the Bayes rule. For the independent events, I'm going to leave that to you. So before we go into Bayes rule, I will review just a little bit about the conditional probability because the Bayes rule is indeed based on conditional rules. Okay, this was what we looked at last week. So don't worry too much. It's not that complex, but the main point that I would like to show here was that if you recall, when we were computing any type of probability, we want to, any type of probability, say PA, whatever event that is, we have a fraction, and what we have here is called our favorable events. And the one that we have as the denominator was our sample space. So here, since we're talking about the probability of event E, given that event F has occurred. So we already have a criteria. We are thinking of the case where F has already occurred. So we no longer want to consider any event where F is not valid. Hence, in this case, we change our sample space, which is our denominator here. No longer is it the entire sample space, but it is only F. We shrink our sample space and we only consider the events that are included in F. And so here our sample space has been changed to F, and our favorable events, since we're talking about E here, we only want to know where E is valid. But since F also has to be valid, we want to know I just blanked out a minute. What's irisan in English?
Intersection, miss.
Intersection, thanks. Sorry, I just blanked out for a minute. So we want to know the intersection, which is our favorable events. So this equation here, I've told you before to please do not forget it, because we will be reusing it multiple times, both in this material as well as in random variables. So this little friend here, please do not forget me. Okay, and we had two special cases in which EF is a empty set, as well as when F is a subset of E. So we also looked at the general multiplication rule, which I will review one more time here, just in case you have forgotten or didn't catch it last week. So the first part here is just me manipulating the equation that I told you to never forget. So here, instead of using E and F, I'm using A and B. So this first part is the one that we already looked at before, and I'm just manipulating it to turn it around. So PA intersection B equals PA given B times B. I'm just manipulating this around. But the point here is that sometimes we do not have this particular probability. But what happens if I were to have the opposite, which is PB given A? It could still be beneficial for us, because if you recall, PB given A, using the equation that I told you to never forget, we would end up with PB intersection A over PA. And as you recall, PB intersection A would be the same thing as PA intersection B. So here we have two exact things. Hello, Afiza, can I please ask you to mute your microphone if you're not question? Actually, I can mute it. Aha, mute it. Can I mute it? Okay. So here we have two different things that are actually equal. We have, hello, where's my pen? We have PBA and PAB. So if I were to manipulate that equation around as well, here I would end up with PBA equals PB given A times PA. Hey, these are the two same things. So I could also write this as PB given A times PA. You will see why this is relevant when we go into the Bayesian rule. Next, if I had a certain third event, PC given A and B, so we can continue on. This is the intersection of all P, A, B. So logically, following the same logic here where I use both conditions, which is B given A as well as A given B, I can also switch that around, and that would give me the chain of events of ABC here equaling PAB given times PC given AB, which I can then translate again to this PAB here. I can translate it to whichever I want. In this particular case, I'm using PA times PBA, which is not the one that we directly obtain, but it's the opposite. And here I can obtain, look at this. This is going this is going A, BA, CAB, and then obviously I can go next to D, D given ABC, and so forth. And thus I can obtain a chain of events starting from starting from A, B given A, C given AB, D given ABC, and so forth. And I can all compute them using whichever way I would like, whichever conditional I would like. So this comes into play when I would like to apply the Bayesian rule. Sometimes you can also find this written as Bayesian law. So this is also sometimes written as such: rule, law, theorem, and so forth. So here we would first like to consider the non-mutually exclusive events. So if I'm talking about E and F, if I want to know in Fasilkom, for example, we have students that know how to drive given that they are male. Next, we also have students that are able to drive given that they are female. So it's very logical for me, if I would like to find out of all of the students that are able to drive, I can sum up those students that are able to drive given they are male, and those students that are able to drive if they are female. And that follows for every type of event. One more example would be like, what's the probability of the international class students having already taken a bath given their camera is on? Here we have, who do we have with their camera on here? We have Jerome, we have Dito, we have Seto, we have Alif, we have Ferdi, we have Bagus. And then the second is, what's the probability that you guys have taken a bath if your camera is not on? See that my conditioning event here is camera on or off. And those are complement to each other, either on or off, on or not on. Thus, for me to compute the favorable event, I can compute it by summing up those have taken a bath given their camera is on, as well as those that have taken a bath, those that have taken a shower with their camera off. So this logic can apply to any type of event. And thus, I can compute the event E, the event that you guys have taken a bath, by taking the intersection of those have taken a bath and their camera is on, and those that have taken a bath and their camera is not on. And if you remember the rule of computing the probability, I can just sum it up because it is there's a joint what's the opposite of intersection again? Union. Union, thank you. Something is wrong with me today. Since I'm talking about the union, if you recall one of the axioms that we covered last week, I can then compute the probability as such. I can sum up the probabilities, and then here I translated it into the conditional. Here I also translated into the conditional. And as you can see here, now my FC, don't forget my complemental F, which is my conditioning event, I don't actually need to know it, because if you recall, the complement can be obtained from 1 minus the opposite. Then I can determine a probability of an entire event based on yes or no, whatever event I'm talking about as the conditioning event. So for a better illustration, I'm going to give an example. So this insurance company believes that people can be divided into two classes. Either you are accident prone, you're clumsy, or you are not accident prone, you're not clumsy. So the statistics show that an accident prone person will have an accident with a probability 0.4. Okay, let's compute what do they mean by this? Don't forget, the first step of answering any probability question, you need to define the events. Here I had already done that for you, and A is the event that an accident will happen, and F is the event of being accident prone. Excuse me 1 second. So now we've already established our letters that I would like to use. Now I'm going to try to translate these probabilities into the numbers that I know. So let's translate the first sentence first. It shows that an accident-prone person will have an accident with a probability 0.4. So this 0.4 that I have here shows a probability of having an accident given a person is accident prone. Is that okay? Everyone still follows? Please just unmute and interrupt me if you are not following. The second sentence says, this probability decreases to 0.2 for a non-accident prone person. So here we know that the probability of having an accident, if you are not accident prone, is 0.2. We assume that the probability of 30% of the population is accident prone. So the probability of someone being accident prone is 30%, or obviously I can translate it to 0.3. Don't worry, I can also compute thus the probability of someone being not accident prone to be anyone. Very easy. I'm waiting.
0.7.
Exactly. 0.7. So following the logic that we just talked about now, just before, if I want to compute the probability of a person having an accident, I can consider the probability of them having an accident given they're accident prone times the probability of them actually being accident prone plus the probability of them having an accident given they are not accident prone times the probability that they are not accident prone themselves. Following the previous slide of the bias rule. And thus we know that, I'm just gonna delete my writing then, that we can compute that probability and we obtain a 0.26 probability of a person having an accident. This is valid for any conditioning, what do you call it again? The conditioning set or the conditioning event being binary though, because here you see there is a probability of someone of event F and the probability of F complement, the probability of someone being accident prone versus being not accident prone, because we need to compute 1 minus PF. This particular case is for a conditioning event that is binary, but don't worry. If the probability that we're talking about was not binary, then I can just add on to it. So here, for example, I have EF given PF, F1 plus PE given F2 times PF2 plus so forth until I have PE given Fn times Fn. But the caveat here is that I actually need to know every single one of these conditioning probabilities. Here, I need to know this explicitly. Oh, sorry. I need to know, ouch. I need to know this probability explicitly. I need to know this probability explicitly, and so forth. But if I'm talking about a binary case, I can deduce the complement by using 1 minus. Up until here, do we have any questions?
Not.
No? Yes? All good? Is there a question in the chat? Because it's blinking at me right now. Give me a second to check. Oh, no, it's not. Not yet. Okay, so I'm going to continue to Bayes' theorem, which is the meat of conditional probabilities. So following up to what I just said just now about the probabilities not being binary. So say I have a conditioning probability, C1, C2, C3, and so forth. So for example, I know this condition of a couple of things. Sorry, where am I? Say I have multiple probabilities that I already know, and so forth. Cn. Let's say I want to compute the probability of international class students having a Honda car, given that they are in cohort 2020, cohort 2019, cohort 2018, and cohort 2017. So here I have 4 different conditions. So in this case, my C1 would be you are a 2020 student. C2 is the event that the student is a 2019 student. C3 is 2018, and C4 would be 2017. These are also called my prior probabilities. I already know them, and I need to know them explicitly if I have more than 2. Next, if I were to know the probability of you guys having a certain thing given this condition, so having a Honda car given year 2020, having a Honda car given you are from 2019, having a Honda car given you are cohort 2018, and so forth, all of this given the n. This is called my likelihood. Likelihoods. I know the prior probabilities. I know which cohort you come from. I know the probability of having a Honda car given each condition, given each prior probability. So what if I would like to know the opposite? I would actually like to know, if I see a Honda car, what's the probability that it belongs to a 2020 student? What's the probability that it belongs to a 2019 student? And so forth. How can I compute the other way around? We can also call this our posterior probabilities. So here we already know the probabilities one way. Now I would like to know the other way around. Oh, I need to delete my writing again. So sorry. So now we already have our prior probabilities, our likelihoods, and our posterior probabilities is what we want to compute. P, C1, P, Cn, we have PA given C1, PA given Cn. I'm sorry if you can hear that. There is a cat meowing right outside my window. Apologize. So this is what we want to compute. Exactly this is what we want to compute. So then how can we compute it? We have to keep in mind the initial equation that I talked about, the conditional probability one that I told you never to forget, as well as the Bayesian rule, sorry. So what do we have here? Let's try to translate our information here. We already know that PA given C1 equals PAC1 over PC1, correct? This is my initial equation of probability, of conditional probability that we love and we would like to not forget. Here is my main idea here. And next, sorry. And next, after I know this, based on the manipulations that I have already learned, I have PAC equals PA given C1 times PCI. Or I can also compute this. If you recall, there is the opposite, right? Remember when we were manipulating this? I could also turn it around as such. Hey, did you notice this? Did you notice that this is actually exactly what we are looking for? This little friend here is what we were looking for. This is exactly what we would like to know. So if I were to manipulate that, I can now compute, C1 given A, which is equal to PA C1 over A. Now, from all of this, what we do not yet know is PA itself, this one here. We don't know this at all. But do you remember that we could compute the absolute probability of A by summing up all of the components that build up into it? And we already know each of the conditioning probabilities. So I could compute PA by summing up PC1 given, oh, sorry, I think I have the opposite here. Let me erase it. Let me erase it, sorry, my bad. I have it the other way around, yes, I do. I can compute it by computing A given C1 plus, oh, sorry, times P C1 plus PA given C2 times P C2 and so forth. And the PA C1, although the PA given C1, apologies, I already know them. PC1, I already know them. So I can compute PA here in order for me to compute either this, to compute this one over here. So here is just a nicer compilation of the equation. It's probably easier to look at than my handwriting. So here we are manipulating these two parts that we don't know yet by using both the bias rule as well as the conditional probability equation, and thus we can compute the posterior probabilities as follows. To illustrate my example, I have this answer here. It's not going to be that complex. We are only having two prior probabilities. Let's try to translate it together. So here, for a multiple choice test, the probability that the student knows the answer is 0.4. Okay, the student knows the answer. What's that? P knows the answer. I have my events down here. Don't forget, this is an important thing to do. PK, right? It's the absolute probability of a student knowing the answer. We have PK. Next, because it's a test, right? It's a multiple choice test. Sometimes you can even guess the answer without actually knowing what it is. So let's assume that a student that guesses the answer, that means they don't really know the answer, but if he gets the correct answer, the probability is 0.2. So here is the probability of the student getting it correct, given that they do not know the answer. They're just guessing, 0.2. So what we're asking is, what's the conditional probability that the student knew the answer to a question given that he answered it correctly? So my condition is that he actually answered it correctly. What's the probability that he actually knew the question? So based on the Bayesian theorem, I know that this can be computed by PKC over PC. So this is the original conditional probability that we must never forget. So PKC itself can be computed by PK given C times C, which we don't know yet, or the opposite, which is PC given K times PK, and the sum here, PC given K times PK plus PC given K complement times K complement. So here we notice that we actually don't know this one here. We don't know PC given K, but we do know that these events are complementary. We don't have multiple options. We only have yes or no. Thus, I can deduce from my previous known information that K complement is 0.6 and PC given they do know. Anyone? This is the tricky part. Let's try to make an educated answer on what is the probability. Listen to my sentence carefully. What's the probability that the student gets a correct answer if he knows the answer? You know the answer, right?
1.
Exactly, 1. So sometimes students often get a little bit confused here because I have experienced some of the students for this particular example answer 0.8 for PC given K. Don't forget that I can only do 1 minus if it's an absolute probability such as K, but I cannot do that for a conditional probability. So that was a little bit intentionally tricky, so please be careful. So now I can just plug in the values that I already know. This is K1, K0.4. I actually think I've already done it. Let's see. Yes, I've actually already done the computation on the slide. And here we have the answer. Any questions? While we are waiting for the questions, I'd like to remind you that this material is for independent study. The basis of the premise is that if it fulfills the independent equation, if the multiplication of 2 events fulfills, then they are independent. If they do not, if you cannot fulfill, then it is not independent. Okay, oops, sorry, I did not intend to do that. So now I'm going to continue to random variables, and while we're waiting, if there are any questions, I'd like to direct all of you to the chat, and I would like to take, wait, what date is it today? 6th? I would like to take the presence of today. Please write present on the chat room, and I'll record your attendance today. Okay, while you do that, I'm going to continue to random variables, but let's take a short break. My clock says 14:13. I'll start again in about 3 minutes. Feel free to take a stretch. I'll see you in about 3 minutes. Don't forget to write your name or present in the chat box for attendance for today. Okay, everyone refreshed? Hopefully. Okay, so I don't know how ambitious I can be with this material today. I would like to finish all of the material today because today we're going to talk about the main idea of random variables. What are they? How can we define them? And then the next material would be, we're going to look at some special random variables, both discrete and continuous. So I'm trying to get the main concept down pat this week. So next week we can go into the special ones. But if I'm not able to, then we're going to have to continue it next week. The thing is, you guys have already, the homework 2 has already been released, and it covers the material of random variables, this whole slide. So you can probably refer to the slides for now. I'll try my best to get as much done as possible, but I do hope that it would be sufficient to help you guys finish your homework. Any questions before we start? If not, I would like to remind you about a question that I believe was posed by Afrizal last week. Is Afrizal in front of his computer right now? Wait, his name is Afriza, sorry, not Afrizal. Apologies. So I believe last week you asked me, like, we have all these axioms and we're computing the probability of something to be equal to 3, for example. But what happens if we have continuous variables? I think you asked me that. Am I remembering correctly?
I am not remembering.
Was it not you? Did I remember the wrong guy? Does anyone else remember? Like, Does anyone feel like they asked me the question? I think it was Afriza, but I could be wrong. No? Okay, so this is the problem of online learning. I usually have in the international class program, there's only around 20 people. So by now I would usually already memorize all your faces and your names. But since we're online, I don't see you that often and I don't really know your names yet. So apologies. So I remember someone asking me last week, so all of these axioms are valid, like if I can sum them up, if they're mutually exclusive and so forth, that would make sense if I'm talking about events that are discrete. Like I have heads and tails. I have on my, what am I calling? On my dice, it's 1, 2, 3, 4, 5, and 6. They're all discrete events. But what happens if I have a certain variable that can be measured continuously? Like what's the probability of rainfall today in Bogor being about 2.3 millimeters? How can I compute these probabilities if I'm talking about a continuous variable? So we're going to look into random variables. There are two types of random variables, both discrete as well as continuous. I believe that the question last week, I think at the time I answered, I'm sure it can be computed, but I'm not really sure how. I do believe that that type of scenario can be handled using random variables. So let's just continue. Once again, we're going to talk about dice. Don't forget, don't get bored of my dice. So I have two dice. Wait, dice. Anyone, you guys are good at English. Is it dice? Like, what's the plural of it? I was like scratching my head when I was making these slides. One dice. I Googled it. What's the plural of die? Anyone? I have a chat. Dices? I don't think so. I don't think you use S. Singular is die, Avatar said. So what if I have two die? Dice. Okay, I'm going to correct that right away. Thank you, Avatar. So dice is already the plural form according to Avatar. Thank you very much. So here I have two dice and I want to consider the event in which the sum of both dice equals 7. So in order for me to equal 7, I have to roll 1 and 6, 2 and 5, 3 and 4, and so forth. But since I am considering the event that the sum equals 7, I actually don't really care which one comes up. I don't care if it's 1 and 6. I don't care if it's 4 and 3. I don't care if it's 5 or 2. What I care is that they both sum up to 7. So so sometimes I don't want to know the details, but I need to know some numerical quantity, some number, some quantitative measure that is determined by the result. So in this case, I could use another way to define my events using random variable. Here I'm going to underline some important parts of the definition. So a random variable x is a function that assigns a number to each outcome of an experiment. So if I have a sample space like this, I have all of the outcomes in S. Say in the previous example, this would be 1 and 6. This would be 3 and 4, and so forth. I don't really care about that anymore. But instead of that, I would like to map each of these outcomes to a certain number. So for example, if I'm I'm tossing 3 coins and I give a number 1 if it comes out heads and 0 if it comes out tails, then all of my possible outcomes would be like this. S000, S001, and so forth. Instead of actually figuring out what the outcome is exactly, like I don't really need to know it's tail, 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 heads. I don't really want to know that. But I want to know my random variable X is the number of heads in every toss. So then I can map these this outcome 0, 0, 0 to a number 0 because there's 0 heads. Here I have 3 outcomes 0, 0, 1, 0, 1, 0, 1, 0, 0. I map that to the number 1. Keep in mind here that the mapping between the sample space and the number is not a one-to-one mapping, because here you can see that I have 3 different outcomes that I'm mapping to one numerical value. So since it's not a one-to-one mapping, the probability of each and every outcome is also not equal. So here the probability of me obtaining 0 would be 1 over 1, 2, 3, 4, 5, 6, 7, 8, 1 over 8. The probability of my random variable being 1 would be 3 over 8, and so forth. So these types of mappings to random variables, I can either describe it discretely or I can describe it continuously. So obviously, when I'm talking about discrete random variables, then I'm talking about a finite number of values. Once again, usually in class, they're like, I'm talking about discrete random variables or continuous random variables. That's a good way to remember. And this happens in sequences, like just now what I explained, like heads and tails, as well as tosses of coins. From these discrete sequences and events, then I can obtain a discrete random variable. For my continuous random variable, I can use infinite and uncountable number of values. So this would address the case that whoever asked me last week, I still think it's Afriza, but I don't remember for sure, asked me, so what happens if I have a continuous value? So for a continuous value or continuous measurement, I can consider a continuous random variable. Keep in mind that if I'm talking about a continuous random variable, I might not be able to compute an exact number like x equals 1.1. No, but I can compute an x being larger than 1 and less than 2. Keep that in mind for now, because here it already came out. It's an interval. We'll look into that more detailed later on. So first we have discrete random variables. Exactly like the previous example, I have, apologies to Avatar, I have not corrected these slides. I will. Okay, there we go. So when I throw 2 dice, I could obtain these results. Makes sense, right? But I don't want to know the details, but instead I want to compute the sum of 2 fair dice. Just like the previous example with heads and tails, I now want to compute x equals 2 and so forth by mapping every single possible outcome to a number. So here, 1, 1, I map to 2, and so forth. As I mentioned before, as you see here, I'm mapping only 1 outcome to 2. I'm mapping 2 outcomes to 3. I'm mapping 3 outcomes to 4, and so forth. So the probability would also not be equal. And this probability that I'm talking about here is also called the probability mass function, PMF, which is defined by the probability of a value is the probability of my random variable having that value. So the probability in this case, the probability of 4 would be the probability of my random variable equaling 4. Oops, sorry, P. Keep in mind, this correction that I just did matters because here I'm using a small p, and this is, and here I'm using a big P. This big P is the PMF itself. This is the probability. So first step, when you're defining a random variable, you must define what your random variable is. For example, X here is, what was it just now? Sum of two fair dice, sum of two fair dice. And then I can define small p, small x, which is a value, equals big P, my random variable equals that value. There are some conditions that must be fulfilled by your PMF. You can go through them yourself. There are some properties that they must fulfill. First of all, they have to be between 0 and 1. Of course, that rule we already established from the beginning. And it also must not be 0 because we're not going to compute those that are equal to 0. And next, we have the values must be finite or countably infinite. And this property must hold. Remember this? The sum of all possible outcomes must be equal to 1 because this equals all possible outcomes to equals my sample space. And my sample space has to equal 1. We already discussed that in the axioms of probability. So now we're going to try to plot. Let's say I'm going to try to, I'm going to try to write it down. So consider a random variable x that is equal to 1, 2, or 3. I don't really know what that means yet. I just know that my random variable is x and it can equal 1, it can equal 2, and it can equal 3. We are given the PMF as such. Note the big P and the small p. It equals 1 over 2, 1 over 3, and 1 over 6. So if I were to be asked, if I were to ask you to define my PMF, then I would need to write it as such. I can use a table. What possibilities do I have? For each value, what do we have here? 1, 2, and 3. What is the probability? I could use a table, half, a third, and a sixth. Or I could actually just use a graph. This is actually the same like what we've been talking about in the beginning of descriptive statistics. We can have multiple ways of plotting our data. So here, if I have 1, I have 2, I have 3, then my probabilities would change. This is a half. This is a third. Of course, it's not exact. And a sixth. I hope I'm correct. Once again, I need to erase that. These are two ways that I can present a PMF. Sometimes you use tables, sometimes you can use graphs because writing them down one by one, which is given here, is not usually the most effective way to communicate your probability. Keep in mind that this is fulfilled. The sum of all possible outcomes equals 1. So keep in mind that we must fulfill this criteria. But we are not always interested in a certain number. I already mentioned this before. Like sometimes I don't really care if it equals like my dice, for example. I don't really care if it equals 2 or 3. But when I'm gambling, for example, I need to obtain a number less than 3, for example, just as an example. So sometimes instead of using a certain number, here it's equal, right? Sama dengan. So a certain number is what I'm trying to compute. I could alternatively compute a cumulative distribution. You guys remember what cumulative means? I'm summing up until a certain point. So alternatively, I could also compute the probability fx here of x. This is a value, right? Small x. So here, if I have fx of 4, then I want to know the probability of my random variable having a value less or equal than 4. This is called a cumulative distribution function, CDF. Don't mix them up. By now we have two: PMF, probability mass function, CDF, cumulative distribution function. So cumulative distribution function wants to compute the probability of a range. So not only do I want to know the exact probability of my random variable equaling 4, I want to know the probability of my random variable cumulatively up until 4. I can define it as such. Don't worry if I want to know. So just now, the range that I'm talking about here is up to a certain number. So I have a top boundary, but I don't have a bottom boundary. What if I have a bottom boundary and an upper boundary? No worries, I can also compute it. So the probability of X being under B would be a probability of X being under A plus whatever it has between A and B. So if I switch that equation around and I would like to obtain the probability of A between B, then I can just compute the CDF of B minus the CDF of A. This is necessary because sometimes you know the CDF, which is cumulative. Like so here, if I have a number here, I know the CDF, so I know up until 10, for example. And since I know the CDF, I know the values up until 3. What if, so this is 3 and this is up to 10. So obviously, if I would like to know the probabilities of, the cumulative distribution between 3 and 10, I can just minus the probability, distribution, of 10 minus the distribution of 3. So these are some basic properties of your CDF. Your function that you use to describe your cumulative distribution must follow these properties. I won't go into them one by one because this is calculus. You've heard this before, monotone increasing function. You must have heard that before in calculus. What does that mean? Anyone? Calculus 1, I believe it should have came up. Even if you don't remember calculus is in English, you should know what it means. It goes up or down. Somebody is chatting me. Function is up. Yes, that's right. By the way, why can't I hear you guys? Are you just not talking? Because on my screen, a bunch of you are not muted. Oh no, you are muted, sorry. It's hidden by my menu, not bad. Okay, Sadam answered via chat. Function goes up and monotonously. So function is up is quite clear. What does monotonously mean? Monoton. Anyone? Sadam, you want to add on to your answer? What do you mean by monotonously?
Repetition, I don't know.
So it does not ever change. It will not ever be straight. It won't go down. It will be monotonously, like it doesn't change. Like, you know, when you're hidupku monoton gitu, berarti nothing changes. So it always goes up. So here I know that the cumulative distribution of a certain number would always be lower than the cumulative distribution of another number if my T1 is less than T2. It will never happen that the cumulative distribution function of 5 is lesser than the cumulative distribution of 2. That would never happen. And the limit that is going to infinity would be as follows. Remember limits? You're approaching the number from the left or the right. Here, since we don't have a limit, like we don't really have boundaries, So I have a cumulative distribution function up until 1, cumulative distribution function up until 10, up until 1,000,000, up until 3,000. I could define it. But since we have some rules about probability that should be between 0 and 1, so we can define the limits, x approaching minus infinity should be 0, and x approaching infinity equals 1. CDF is right continuous. This has something to do with the formal definition of limits. You must have covered it in Calculus 1. There is like, if I recall correctly, there's like the formal proof and so forth. You should have covered that in Calculus 1. Next, for a discrete random variable, as you can see, in a discrete case, since we're talking about a certain, so we're talking about numbers, right? We're talking about a certain number of values. If I'm talking about the probability of my random variable being less than equal to a certain number, say 5, I can just sum up equal to 5, equal to 4, equal to 3, and so forth, because it's discrete anyway. And this is what it means here. I can just sum up the PMF of every single value that is lower than my limit. So for a discrete random variable, it's very, very straightforward. I have to be able to define it formally. So since it's cumulative, don't forget, like for less than 1, there's no way my possibility, I don't have a probability lesser than 1. So that would equal to 0. Between 1 and 2, note that 1 is included, but 2 is not. It follows into the first probability, and 2 to 3, it's 1/3, but it's cumulative, remember? So I need to plus this and that, and so forth to A is larger than 3. So larger than 3, we no longer define it, so it must just stay at 1. So if I were to graph it, can I graph it? I think I can graph it. Yes, actually I can graph it. So since it is discrete, then what comes up is a step function. So here it's just 1/2, and then it starts 5/6, and so forth. And this will never go up again. It would just go like that. So don't forget that these are some graphical notations that you should already know. So here, since I have an empty circle, yes, an empty circle here, that means that this value, it includes 1, but it does not include 2. If you remember, here it includes 2, but it does not include 3, and so forth. So please be careful with your notations here. That's why you should remember your calculus. So up until now, we've looked at 2 different functions that are used to describe the probability, the probability distribution. We have PMF and we have CDF. Don't forget that PMF is the probability at every single discrete point. The CDF is the probability up to a certain point. So PMF, obviously, since it's at every point, is only valid for discrete random variables. Whereas the CDF, it's up to a certain point. So I could use it for discrete variables, but I could also use it later for continuous random variables. We'll see how that works in the next subchapter. And the relation between PMF and CDF can be described as follows. Any questions? I'm going to take a small drink break. Questions are welcome. Okay, not yet. Fair warning, a lot of calculus is coming up. Who loves calculus in this class? see a lot of nervous faces. Anyone? Come on, call out your friends. Who's the calculus nerd in this class? Afriza turned on his computer. Is it you? Are you the calculus nerd? No? Are there no calculus nerds in 2019? Okay, there's a chat. Somebody's throwing someone under the bus. Bagus, Bagus. Oh, we have Bagus here. And his camera is on. Okay, Bagus. Do you remember a lot about calculus? Saddam says, oof.
I think
Saddam
so,
wants
Miss.
to- You do? We're going to have a lot of integrals coming up and exponential functions. Straight A's. Okay. Okay, so I would like to clarify some stuff. You do need a basic foundation of calculus to follow this next chapter. But I would like you to remember that the main point of this course is not to do integrals. That's Bu Aruni's part. So if in the future, in the midterms or exercises, you might need to be able to solve the integrals, but don't worry if you can't, because I will also be grading you in your ability to translate the particular events we're talking about into a probability function, and not only you deriving the function. So like if you can translate it correctly into the correct form, but you can't simplify it to the best form, don't worry, you will get a grade. I won't just say it's wrong, because I would like to reiterate to you, you do need a basis, but that is not the point of this course. Okay? So please don't get scared yet. Okay, so for continuous random variables, we're gonna get a little bit more complex, because as I mentioned before, for PMFs, it's equal a certain number, right? For CDF, I'm calculating up to a certain point. If I'm talking about continuous random variables, I cannot use PMF. I could use CDF, but there is a better way to do it, which is a probability density function, or PDF. There are multiple slides here, so please try to follow. So a PDF starts with the assumption that if X is a continuous random variable, so it's a random variable that is mapped to continuous functions. So my outcomes are mapped to continuous functions. Continuous values, apologies. So when my outcomes are mapped using a random variable that has continuous values, there exists a non-negative function, fx, defined for all real values for any set B of real numbers. So let's translate it to this mathematical function. So this function, I need to define a certain function that must be non-negative, that can describe the probability distribution of any value x between negative infinity to infinity on a certain interval B, a set of any real numbers. If I can define that function, this is called the probability density function. Still talking about the probability density function, didn't change. So now we know what this means. We know that we're talking about this non-negative function. We know we're talking about the values of small x, and we know that we're talking about a certain interval here. So the probability that my random variable will fall into this interval will be computed can be computed by taking the integral over this particular interval. So if I define my upper and bottom boundaries of my interval, I can then translate this equation on top to this one here. So the probability of x being between a and b is the integral over a and b of the PDF. This is an integral, and if you remember what is actually an integral, The integral is the area under the curve. So I just need to compute the integral to obtain the area of curve. So for example, I need to find a function, say this is fx, and I want to compute the probability of my random variable being between a and b, then the probability is that area there. So in order to do that, I need to define a certain function. This function fx here has to be such that it fulfills this first criteria. The integral over all possible values. Here. So if you remember, the sum of all possible outcomes must be equal to 1. We've already talked about that in the axioms as well as the PMF. But in a continuous random variable, I can't really define all of the possible points. So here we use an integral over negative infinity to infinity. It must equal 1, which represents the probability of everything that may happen, and which is our sample space. If you remember that the sum of the sample space must equal 1, then based on the same result, the same equation on top, if A equals B, so my lower boundary and my upper boundary of my integral. So if we remember calculus, so here is my function, fx. If my starting boundary is A, and my stopping boundary is also A, then what's the area under the curve? Jerome is going like this. What does that mean? What's
There's
the area?
no area whatsoever.
There is no area, exactly, because those lines are intersecting each other. Thus, based on the definition of an integral, then a certain probability equals a certain number. The probability that my random variable, equals a certain number is 0. This means that the probability that my continuous random variable will have a specific value is 0. So if I go back to the question that I still think it was Afriza that asked me, but someone asked me last week, that how can I compute the probability of a certain variable equaling 1.1, 1.3456? It will be equal to 0. Because we assume that the probability of a certain value cannot be determined, so it's equal to 0. I can, however, predict what's the probability of my random variable being between 1 and 2. What is the probability of it being 2 and 3? I cannot pinpoint a certain value. So there are some properties of the function itself that must hold for the PDF to be used as a correct description of the probability. So first of all, unlike PMF, the PDF is not a probability, because what it means is like this. Since the probability of every single event should be between 0 and 1, then the probability between 0 and something, not 0, let's say A and B, is a sum of all of these individual events. So if I sum them up, they can equal more than 1. And it must be larger and equal to 0, because if you recall, the first criteria of a PDF is that it must be a non-negative function. Next, since the continuous random variable is mapping my outcomes to an uncountably infinite set of real numbers, then I know that for any small event that's in the middle of it, so any interval A and B that is between negative infinity to infinity, each interval must have a probability between 0 and 1. And that if I were to sum up all of these events from negative infinity to infinity, it must equal 1. So before, we already looked at the relationship between PMF and CDF. Now, CDF and PDF. Very straightforwardly. Remember cumulative distribution function? Let's try to define it. When we were talking about PMFs, I'm talking about the probability of a certain point. When I'm talking about a CDF, I'm talking about the probability up to a certain point with no limit at the end. And when I'm talking about PDFs, I'm talking about between two certain points. So here, when we recall those properties, we know that what's this? We know that my cumulative distribution function is actually just the same thing. It's a PDF, but the bottom limit is undefined or negative infinity. Because here, it's quite clear for my CDF. Let me write this down so you guys can know what I'm talking about. PMF, CDF, and PDF. So my PDF has clear boundaries, but my CDF does not have a boundary on its left, on its bottom. So we use negative infinity. So the relation between the two, since I'm using integrals, so if I would like to obtain the CDF from my PDF, then I need to integrate it. What's the opposite of integration? Bagus?
Differentials.
Exactly. So on the other hand, if I want to obtain the PDF from CDF, I would need to differentiate it. That is the relation between the two. Okay, drink break for me and for you guys, please take a look at this question. Okay, any ideas? You remember that we had some criteria for a valid function to be used as a PDF. I'll help you out for now. There are two things that we need to check in order to determine if this function is a valid PDF or not. First, since we have to use a function that is non-negative, then we need to check first, is fx always positive? Second, is the integration over the valid range equal to 1? So let's look at the first one. Is it always positive? Let's see. So for x less than 12.5, we know that it's equal to 0. That's fine because I need to have fx must be larger or equal to 0. So this part, fine. So now we need to know if this is always positive for x equals to 12.5. Let's look at x equals to 2.5. So x less than 12.5, it's fine because it equals 0. X equals 12.5. Let's try to plug in the values here. We would obtain 20e to the power of minus 20 x 12.5 minus 12.5, so 0, right? 20 to the power of negative 0. Anyone remember what is e power 0?
1.
1, that's right. So this would be definitely positive. Obviously, if it was not 12.5, but instead it's larger than 10.5, I would still obtain a positive value here. So we know for sure that for all possible values of x, fx is positive. Next, the next question we need to answer is fx valid over the valid range? Sorry, is fx over the valid range? Does it equal to 1? Does its integration equal to 1? I do believe that I have written it here, which is a lot easier to read. So yes, if you want to follow this derivation, so I can consider, what I need to consider is the range between 12.5 to infinity, because I know for under 12.5, it would equal to 0. So it wouldn't add anything to my integration. So feel free to go through this, but it does equal to 1 because at the end, I end up with e to the power of 0. Once again, I would like to reiterate that your job in Statprob class is not to derive this. You still need to be able to do it because you need to use your pre-knowledge of calculus. But if you, for example, only get up to this point, you would still get maybe half of the points, because Statprob is about translating the event into this equation, but the derivation itself is calculus. So please don't be scared if you can't derive it fully. So here are just some additional properties of the cumulative distribution function and its relation to the cumulative distribution function and its relation towards the PDF. Since we can use both CDF and PDF for continuous variables, some problems will give you one or the other. Based on what? Just based on whatever I feel like giving at the time. So since we already know the relationship between the two is an integration and differentiation relation, then I can obtain some particular identities that follow, that are shown in this part here. We have two identities that I can compute between two intervals using not the PDF, because the PDF is definitely an integration between two limits, but using the CDF instead. So based on that logic, we have this question here. This is the previously defined PDF. So here we have the PDF of the continuous variable. We already looked at this before. And the question asks you to determine the CDF of x, which is the big Fx. And then we want you to compute the probability of x being between these two values using Fx. It's explicit, right? Because if I don't want you to use CDF, you can just simply use the PDF itself. So here I can just do 12.5, 12.6, 20e minus 20 x minus 12.5, sorry, dx. Because here I'm using the PDF. We know that a PDF is defined between two numbers, so it's very simple. But this question asks you to actually use your Fx or your CDF. So let's look at how to do them. So first, they want, I want you to define the fx, the CDF. Sorry, so this is my CDF. What I already know is my PDF. What's my PDF? I do believe I wrote it down here. Yes. My PDF that's already given to me is 20 e to the power of minus 20 x minus 12.5, I think. Yes. Yes. So this is my PDF. If I want to obtain the CDF, what I need to do is integrate it. So fx, or don't forget, fx is, PDF is a probability of a certain point, CDF is a probability up to a certain point, and PDF is a probability between 2 points. So when I'm talking about CDF, then I need a probability up to a certain point. So this probability of my x being less than and equal, sorry, this is the wrong number, x being less than or equal a certain number. So here I can define my limits being negative infinity up until certain number, 20 e. I cannot use x here because here I'm using x. So let's use a y here instead. 20e minus 20 y minus 12.5, I believe, dy. And here starts the calculus because I need to be able to integrate in order for me to solve it. We'll look at the solution next. And for this part, in order for me to obtain this probability of 2.5 x 12.6, if I'm talking about my CDF, which gives me a probability up to a certain point, if you recall, this would give me the probability of up to 12.6. Probability of x being less than and equal to 12.6 minus the probability of x being less than and equal to 12.5. If this doesn't seem clear to you, once again, I'm going to draw the line. So if the first one, the probability of x being less than 12.6 is this, and the probability of x being up until 12.5 is that, then if I want to know the probability between the two, obviously I just do 12.6, the red part minus the green part. And this is what we just did exactly in this part here. So I've already pre-computed the answers to this. So we already started this out. We've already started this out using this equation here. And we mentioned that I'm trying to compute the values up until x, but starting at negative infinity. But I already knew that my PDF is valid for x's that start from 12.5. So I can change my bottom limit to 12.5 here. And then it can be solved and I obtain a function of the integrated function, which is this one. Don't forget that when I define a CDF, I have to be able to define it on every single possible value of x. So here I know that for x larger and equal to 12.5, this is the function here. I just rewrite it here. And less than 12.5, it equals 0. And thus, since I already have this function here, so now I can compute the function of 12.6, just plug in the values here, minus the function of with the values of 12.5 here, and I can obtain this answer here. This is just a representation of the graph. Keep in mind that a PDF is a function that is just non-negative, whereas a CDF must be monotonously going up. So here it's proven with these functions. The integration or the area under the curve equals the CDF. This is what is intended in this part here. And that's the end of the calculus portion of today. No more for now. Any questions? Okay, enough with the calculus. Let's go back to basic numbers. So the next part is, up until now, we've only assumed that the values have one possible value. But what if we have we're only talking about one random variable. What if I have more than one? This brings us to the jointly distributed random variables. I'm not going to go too much into the rules, but basically when I'm talking about a PMF of a certain random variable X, the PMF is the probability of my random variable having a certain number. Remember, this is a PMF, is an exact number. So if I have two random variables, one is X and maybe one is Y, this is Y and this is X, then if I would like to compute the probability of both of them fulfilling something, so here I have probability of X equaling something and Y equaling something, this defines my joint probability of P, A, comma, B. And here it's just the reiteration of this joint probability mass function, where the probability of A comma B is the probability when X equals A and Y equals B. So the logic is that when I'm talking about the probability of X only, and I were to know the joint ones, I don't really care what Y, what the value of Y is. So I can just sum up all of the possible Y values. And on the other hand, when I'm trying to derive the probability of Y only, I don't care what value X has. So I can just sum up all of the possible values of X. I can write it both in PMF, I can write it in joint cumulative distribution as such, and thus I can use a certain method or table to describe the joint ones. So this particular example, I'm going to leave it for you to read on your own. But basically what happens is I need to draw a graph of all of the possibilities of the first variable and all of the possibilities of the second variable. So if we know that the first variable has the values of 1, 2, 3, for example, and the second variable has the probability of 1, 2, and 3, I need to be able to compute what is the probability that X equals 1 and Y equals 1. I need to know 0.3, for example. And what's the probability that X equals 2 and Y equals 3? Maybe it's 0.7. I need to be able to compute every single one of them. So in this particular case, it can be translated into a graph like this. We can look into more details. Like I'll probably open a forum for you to discuss, where does this number come from? It's a permutation of something. So if I already have the table, then it's easy for me to compute these two questions here. What is the probability? What's the joint probability of 1, 1? So 1, 1 means I must equal 1, J must equal 1. Which one is it? Quite straightforward. 1 and 1. Should be this one here, right? Yes. So here it's 60 over 220. Next, I should use the same color, shouldn't I? So sorry. 1, which is this one. 1, 60 over 220. The next question, I'm going to use a different color. So what's the probability that y equals 2? So when I'm only considering one variable, in this case y, I don't care what value x has. So in this case, I only want to know y equals 2. I don't care about y, so it's just the sum of everything here, which is already computed this one, and it's 48 over 220. So up until here, we have looked at how we can use both the PMF and CDF to compute a joint probability. Obviously, if we have continuous random variables, we can also look at the joint probability density function, which is a double integral of two different variables. I don't think I want to rush through this at the end of this class because I'm looking at my clock. I'm already 15 minutes late. I apologize. So I'm going to leave you at this slide, the joint probability density function. I think it's quite straightforward how we can describe the joint using PMFs because PMF is discrete. CDF is also quite straightforward because it's continuous. But here we have more calculus. So I'm going to stop it here. We're going to continue next week from the joint probability density function and its exercises. Once again, we also have independent random variables, which I'm going to leave for you to read on your own, but I owe you this small part of the joint probability density functions. Any questions? No? Really? Are you sure? Okay, so as a recap, I'm going to stop the class at this table here. If you've already accessed the slide on Scale, we're stopping at this PMF here. I'm going to let the assistants know that we've only arrived to this point. So in regards to homework, if there's something that you cannot solve up until maybe it's after this point, please let the assistants know. I'm going to tell them too that we haven't covered up until the end. Any other questions? I'll start here, okay? Next week, sound good? Okay, I don't want to rush it. Okay then, we'll look at this part next week. And I guess that's it for this week. Does anyone want to share anything non-Statprob related just to clear the air after all the calculus? No? All good? Okay then. So I'm going to leave you on that. Please don't forget to do your online activities, one exercise, and homework. It's not the end of this week. Homework is for next week. So that's it. I'll see you guys again on next Tuesday, and I'll start off on the joint probability using PDFs. Thank you, and wait, give me a sec. Let me stop the recording.